Do you have a pen? The washing machine is delivering this week. Everything working fine?
Yeah, I think so.
So what you will need?
Yeah, I don't know.
The laser pointer.
Laser pointer and I will do my forward, backward move.
Yeah, the presenter. So this is the microphone which is only for the recording. So the recording is already prepared. You only need to start.
Yes. Yeah, is yours okay? In any case,
I mean, in case I could bring another one.
no,
It's okay.
Oh.
It seems to have been changed.
Yeah, okay. Okay, sorry.
L'abbiamo in internal, so...
No, you are the graduates of people not reserving coffee. The principle. Oh well.
What means couple this tree? National capital city.
It was the first governor of Greece after the Ottoman Empire. So,
Okay.
1827. He was the first one that founded the first university, which was this. So it's the oldest university.
The oldest university in Greece.
Yeah, I mean, after Ottoman Empire, where we had 400 years of
Yeah.
evolution.
Wonders.
Enough adrenaline, blood.
You already connected the
I try to not to move. I will be around here, so you're going to be. Entonces los otros dos que los otros que no te han escrito todavía.
No, es que me han escrito. Les he dicho que le acabo una semana más.
You started a bit later today because
¿Se ha salido este?
Sí, los de otros dos.
¿Este primero o otro?
Debe estar antes.
No, porque aplazamos con el que ya, después vamos a tener a todos lo mismo.
Claro.
Welcome to our today's seminar. It's a great pleasure to introduce our today's speaker, who is an internal speaker from IFISC, Apostolos Argyris. Apostolos joined us as a Marie Curie Fellow in July and will at least stay for the next 2 years with us. He got the project Centurion accepted, which is on signal processing and optical communication networks using reservoir computing. And we're very much looking forward to working with you on that. Apostolos is a very senior scientist with a lot of experience in optics, photonics, optical communication, complex systems. And he has participated in quite a number of national and European projects, some of them like Occult and Picasso, even with members here in IFISC. He received his bachelor degree from the University of Thessaloniki in physics, then a master's degree in microelectronics and optoelectronics from the University in Crete, and then he moved to Athens, where he is since 2001 at the oldest university in modern Greece, the National and Kapodistrian University in Athens. And then he got his PhD degree in 2006 on the topic of secure high bitrate all-optical communication systems based on chaotic carriers. And that is also where some of you might know him from. He was the first author of the Nature paper that some of members in his co-authored on optical chaos communication. It's worth mentioning that he also has a bachelor degree as an observer meteorologist from the Hellenic National Meteorological Services that he received in 2005. He was between 2006 and 2009 an adjunct lecturer at the Department of Computer Engineering, Telecommunications and Networks of the University of Thessaly in Greece. And it's worth noting that he also received quite prestigious prizes. In 2006, he received one of the world's top young innovators TR35 award, which is an annual selection of the world's top 35 innovators in research, business, and entrepreneurship under the age of 35, which is given usually from the Technology Review magazine of the MIT. He did a lot of excellent work in fundamental complex phenomena, in optical systems and their applications, and we're very much looking forward to hearing some of that today in your presentation. We're happy to have you here.
Thank you, Ingo, for your kind introduction. I have also included some information by myself. I mean, it has been almost 15 years that I first met and collaborated with some of the people here in the audience, with Professor Mirasso, Fischer, and Colette. It has been already 10 years after this nice work we published in Nature magazine under the coordination of Professor Mirasso, and the use of semiconductor lasers and their emitted complex dynamics, where they can apply in modern optical communication systems. And this was one attempt to introduce some hardware encryption level in the optical communications field. This was, of course, in the past. The future, and the reason that I am here this period, that I will be for almost the next 3 years, hopefully more, I don't know, will be this project that has passed. It is named Signal Processing in Optical Communication Networks Using Reservoir Computing. This topic is a little bit relevant to the previous one, since we will employ also the use of semiconductor lasers and make some attempts to see the possibilities of reservoir computing. This is something that is an application field, and I will discuss it a little bit further at the end of the presentation as a potential application of the use of nonlinear dynamics of semiconductor lasers. I proceed with this seminar's talk, which is Semiconductor Laser-Based Networks and Applications. This work was done the last year, affiliated by the University of Athens, where I was until I got here under the supervision and collaboration of Professor Dimitris Sitridis of the Optical Communications Laboratory in the Department of Informatics and Telecoms. So the outline of my presentation, I'll give a short introduction in some principles that semiconductor lasers obey for many of the audience that may not are familiar with. The main part of the presentation will include these topologies, the implementation of coupled semiconductor laser networks with all-to-all connectivity. We will investigate these topologies with a passive and an active relay. I will explain in the next slides what it is all about. Where we can identify experimentally global and cluster synchronization in these setups. Finally, I will give some summary on these two aspects, and I will just give you some highlights on potential applications and what we have tried to do to use these networks as potential applications in optical sensing, optical communications, secure communications, and some future work. This will be probably a topic of another talk. I won't be explicit on that, so I will give you some hints on that. So I start by saying some very introductory things, that chaos generation by semiconductor lasers can be achieved in many ways. You can find that in the literature in the last 30 years. It was very popular, where you could see systems with optical feedback, where semiconductor laser has output, its output reflected back and destabilizing it. This same comes with an optical injection scheme, where two lasers interact with each other. Some optoelectronic feedback configurations, where we have an optoelectronic conversion of the signal of the emitted signal of the laser and feeding back the semiconductor laser, or in more modern literature publications, we have an extension to optical coupled systems, where we can have many semiconductor lasers interacting with each other, forming interesting patterns of nonlinear generation and many times synchronization effects. So based on these properties, I have an example of a symmetrical optical injection between two semiconductor lasers. When the coupling strength is low, the coupling parameter is low, usually all semiconductor lasers behave in a CW operation. However, when we destabilize their operation with a coupling parameter, with an increasing coupling parameter, we can see that we can turn into complex dynamics where we have periodicities or even chaotic dynamics emerging from this coherence collapse operation. One very interesting aspect of seeing the collaboration of independent units that emit such complex signals is the property to synchronize under appropriate and optimized topologies. So when you have uncoupled systems that may exhibit some chaotic operation, these are able to identify them as chaotic generators and emit complex dynamics. However, these dynamics are not synchronized with each other. However, these systems, when are coupled and appropriately put together into topology, the right coupling coefficient makes them operate in a synchronized manner, and this is a property that was first introduced in dynamical systems by Pecora and Carroll in the 90s, and then in the CO2 lasers Sugawara in 94, with Rowe in 94 also for semiconductor lasers. This is an old property. However, in the modern applications, this has been extended to networks also. Let's see now a conversion of these topologies that couple signals with each other, which is the use of a relay system, which is a system that interacts between the outer nodes of what we are interested in, which in our case is the semiconductor lasers. There have been also in the literature several topologies that discriminate this relay being active or passive. Passive, for example, meaning that it doesn't contribute to the system its own dynamics. However, active means that has some active properties that introduce them into the system. It has been shown explicitly in the work of Flunker in 2009 that when we introduce such a relay system, if we use a passive relay, then the solutions of the synchronization manifold that we can observe is transversely unstable, which means that we have short or long desynchronization periods within the synchronization region, referred also as bubbling, introduced in 94, this term. And of course, when we introduced some mismatches in the operation of these nodes, then less and less modes become transversely stable. On the counterpart, when we have such topologies that we have active relays, for example, another semiconductor laser, we can achieve some synchronized behavior without any desynchronization events. In this case, the condition that should be obtained is that the dynamics of this relay are much stronger from the dynamics of the nodes. And this way we can achieve a bubbling separation and even better synchronization performance. An example of such a system that has been investigated experimentally was in the work of Zavora Mund in 2010, probably also known here in the IFISC. They investigated the coupling topology with a relay system, an active relay system with a laser in the center. And in this work, they investigated the contribution of the number of the nodes in such topology in respect to the synchronization or the synchrony, or the crowd synchrony, as they claim, as they introduced that in their paper, where we can see that for a completely symmetric topology with a low number of nodes, up to 10 or 25, there has been not implicit synchronization in the network, while by increasing the laser number in the topology, we can achieve some synchronization patterns within the emitting time traces. Of course, their condition in the operation of this network was to introduce that each node has been diversified from the total sum of nodes by a mismatch detuning in its frequency. And this detuning that was introduced was a little bit large in terms of applications, because when you use semiconductor lasers usually in the optical communications technology. You can tune its wavelength very strictly at the range of megahertz. So this is a property that could be changed. Oops. It could be changed. One thing that one can keep in mind when seeing such topologies and seeing lasers connected with each other, the physical connections that you may have in a system, with a fiber link, for example, does not mean necessarily that you have a connection strength. The link has a strength in this network. What I mean is that this strength is determined, the strength of the link is determined by the coupling efficiency between the two nodes and from the frequency detuning, which is a parameter that gets into the nonlinear, the rate equations of the nonlinear profiles of the lasers. So usually when you see a topology physically connected but detuned in wavelength operation, this might impose some weak links in connectivity within such a network. So I start with the first part, which is the coupling configuration with a passive relay. In our system, we have used as a relay a reflector, and this property that has been, as I said, investigated in Foucault et al. Can be generalized with n outer modes with some detuning in coupling paths in terms of the connectivity, in detuning in frequency emission, while in our experimental setup we have tried to preserve a coupling matrix that is completely symmetric. It is an all-to-all connectivity with an all-to-all matrix here 1 times the coupling strength of the connections between the nodes. So in our experimental setup, we will investigate a laser setup with a network setup with 16 nodes. All these nodes have identical emission characteristics, and this means, especially in two cases, what we mean is that each laser contributes to the reflector, and then in this setup, the reflector turns back every reflection to all lasers, which means that each laser contributes a portion of 16 to all of the lasers. We identify a symmetric operation, which means all lasers are said to have the same wavelength emission, also are said to have the same optical power emission, which means through the fabrication process and the diversities, we may need to bias them a little bit more in current or to make some temperature adjustment in order to fix the wavelength condition.
Excuse me, you said that light, for instance, emitted by number 1 is reflected to all the...
Yeah.
How is that done?
I will show that in the next slide in the implementation. So we have, yeah, as an experiment, we have in one part all the lasers, we have the fiber connections that, of course, are sent through fiber links, coupling different passive and active optical elements up to a tunable reflector, while the vice versa path is followed to split all the injection path to 1 up to 16 lasers. So in this topology, we have an all-to-all coupling setup with, of course, polarization control, which is the most tricky thing to contribute in such a system and maintain the same polarization condition that is reflected then as the same optical injection power for all the lasers. And of course, when you see so many splitting and coupling, it means that you have so many losses within your setup. So you need some amplification stages. This is two unidirectional amplification stages in order to avoid the cross-gain modulation effects if you travel with powers exceeding several milliwatts.
You mean optical amplification?
Yeah, optical amplification. This is a whole optical system. And at the output where we can read the output of each laser is at its output port from 1 to 16. We introduced the injection ratio, which is simply expressing the ratio of the total optical power that is injected to one laser divided by the power that the laser needs. So this is a ratio that is making a symmetric system is kept almost constant for all the lasers, meaning that this is of course a tunable parameter that we can play with by minimizing the injection when we go to practically an uncoupled network, while where we amplify we can get up to an even strongly connected network with strong injection signals going into its node of the system. So I have some pictures that will go fast. There are some PCB cards that we had to put all the lasers in order to have all the current temperature control, some electric filtering in order to reduce noise during biasing. These lasers have been set in some strips of some arrays of 10s. We have been able to build this setup so we could choose 16 out of 40 lasers, and through the appropriate optical coupling, we have the optical coupling here and the distant reflector here, and we have built this system which was amazingly stable in terms of polarization for several days, operating stably. And finally, we have the readout instrumentation where we had 4 photoreceivers of the same manufacturer and a 4-channel real-time oscilloscope operating at 12 GHz, where we were able to monitor at the same time 4 lasers simultaneously, which means that we are not able to monitor all the 16 at the same time, but since you have a stable operating system during days, you can go serially and evaluate all the signals in pairwise evaluation. An example of the emitted signals, how they look like in such a network, you can see already some very complex dynamics. For a specific injection ratio that we will show later, we can achieve a relatively high cross-correlation value of 0.92 for lasers 1 and 2, for example. We can identify some desynchronization events as we expect, since we have a passive relay topology, and these desynchronization events could be minimized. This was the specific task here, to minimize them. This was done by matching as best as possible the frequency detuning and the deviation of the optical emission of each laser.
One question. If you say that the stability, the system is transversal and unstable with the passive mirror, why don't you observe more bubbling here? I would expect to see bubbling everywhere.
There might be a bubbling everywhere, but you can see that this period of time is relatively very small.
Okay.
If you extend that to a larger window, then you can see bubbling. But the contribution of bubbling, you can minimize the duration in terms of unsynchronized divided by synchronized region. This could be up to a 0.8 to 1 or 1.2% duration of the total emission. So this desynchronization can be minimized to an extent that it allows a cross-correlation, an average cross-correlation of 0.92. But there are incidents that avoid you at this period of time to...
But to be precise, globally it's transversely stable. It's only that some unstable periodic orbits are
some period,
transversely
yeah.
stable.
Okay.
So it's globally transversely stable.
Exactly.
One important parameter, as I said earlier, was the coupling coefficient, where we go from one laser to the others. And this made us to make a mapping on the average cross-correlation of specific pairs and also on the dynamics that we observed during this change of the optical coupling. For different injection ratios, you can see that always we have chaotic operation. We were not able to identify some strict periodic or quasi-periodic operation during the operation of the system. However, this could be observed when we went into very large values of optical injection, which means that the amplifications gave enough power in the system and the injected total power in each laser was much more than the one that it was emitting. So in this case, we had the coexistence, the interplay of various dynamics, which was even CW operation, followed by periodic operation, chaotic operation, and then back and forth in this unstable emission. In this case, we observe that the average cross correlation becomes lower, and of course, the variance becomes higher due to the different status of the complexity of their emissions. However, we have identified this region where if we say that we accept a global synchronization average over 0.8, we can identify some injection region where this system operates relatively consistently in terms of cross correlation. Now, in this experimental setup, we have, as I said, we have 4 outputs. So in these 4 outputs available to monitor 4 laser systems, we had made an overall pairwise evaluation of all laser nodes for the full signal bandwidth that we had available from the photodetection. So this was the case for the predefined this injection ratio 0.2, which was around here. And you can see that we had the lowest cross correlation value among all pairs for a specific pair was 0.83, while the highest 0.96. So this is a consistent operation. This can be investigated also numerically, where we have these Langko-Bayashi rate equations, the frequency detuning term, the intra-cavity gain or loss of each laser, the network coupling, and the laser noise for determining the complex electrical field of their emissions. When we try to make such a numerical simulation, we have to make some compromises because the length of the system is hundreds of meters or even kilometers if you employ some transmission length between the nodes. It is not possible to include these delays in the numerical simulation, so we had to include lower values on delays. These values for all nodes were from 9 to 11 nanoseconds. We have introduced some minimum difference in frequency detuning because it is a typical, since it's the resolution of the frequency that we can obtain in this control of such lasers. And you can see in this video the performance of the pairwise evaluation of the whole system as we increase the injection ratio. Now it is implied by kappa. You can see some synchronized operation, then we go to completely unsynchronized operation. Now we have a chaotic emission where all nodes are synchronized, and when we reach the point where we have an enough value of coupling, then we can get to highly correlated emission among all these laser nodes. Of course, we had some this system, the Langko-Bayashi equations consider coherent interaction. So we had applied some random distribution over the phase in order to make an evaluation of a system that has incoherent feedback, since the topology will be nonlinear. We didn't observe any alteration in terms of the complexity and the synchronization of the system in terms of this pairwise evaluation of cross-correlation among all the nodes. This performance has been obtained for a full signal bandwidth. What we had observed, but in this same system, by changing the signal bandwidth and the system bandwidth, I mean the bandwidth that we evaluate at the output of the detection, not the bandwidth that circulates within the optical cavity. And deteriorated that to 2 gigahertz, we had a great improvement in the performance of the system, where the lowest cross-correlation value was 0.92 and the highest 0.98. So the reason for that, that's by filtering to improve this performance, is that we have increased with this action the signal-to-noise ratio of the output signals up to 4.6 dBs. I will give that more information in the next system, in the next topology that we will investigate. Noise is reduced, of course, due to this filtering, And we have another contribution that usually in such instances, when we evaluate synchronization, we know that higher frequency components of such chaotic systems are much more difficult to synchronize in an experimental system.
Sorry, what do you filter here? The direct output from the laser or the measurement?
The measurement, the
measurement.
signal that we measure in order to get this output time series.
Okay, so each laser is as before.
As before,
It's just
nothing was intercepted within the optical system. And I will pass through that quickly. We had also some normalized permutation entropy measurements in terms of feedback to see if this filtering changes the complexity of the signals that we have evaluated. It seems like we do not have any change in the permutation. All signals are near 1. Of course, these patterns are when evaluating filtering due to artifacts from the sampling process, which means that we, for a sampling of 20 gigahertz or 40 gigahertz, if we reduce the bandwidth by 1/8, we should reduce the sampling by 1/8, which means we can see the normalized permutation entropy after 8 neighbors, 7 or 8 neighbors, and this is a measure that we can identify that the complexity is preserved to the previous levels. Now we have made some tricks in this network. For example, we have all lasers set with identical emission, wavelength emission, except from one. So number 16 is now shifted to a variable delay, and what we can see from this shift, if we evaluate the average cross correlation between laser 16 and other lasers or other lasers participating in the network, we can see that for loosely coupled network, which is a low coupling value, we can see that the cross correlation between laser 16 and other lasers drops immediately after hundreds of megahertz of tuning. While if you have a strongly connected topology, then this level of synchrony is kept until a few gigahertz, and then you can see that the cross correlation of laser 16, which is the shifted one, with the rest of the network are again decreasing. Overall, even if you apply this shift to one laser, you can see that there is no influence in the lasers that are remained connected with the same wavelength in the network. In a cluster synchronization approach, where we have now decreased number of the number of lasers that participate in the network down to 8, we have all of them in the same wavelength. Of course, there is a resolution that this wavelength can be tuned. Also, with 8 lasers going down, you can see that we can preserve a mapping of well-correlated signals. What happens now if we shift a quartet of lasers out of 8 in a not far distance of the wavelength, which means we have shifted these wavelengths up to 50 picometers. 50 picometers is a small detuning, it's around 7 gigahertz, when comparing that to dense WDM communications, where usually the optical communications channels allocate themselves in a distance of 50 or 100 gigahertz, which means that if we had such signals in an optical communication system, there will be a huge inter-channel interference among these clusters. So, in this case, we have a discrimination that is not clear. However, when we make this pairwise cross-correlation evaluation, we can see that intra-cluster connections remain connected and synchronized with a very high value of correlation, while intra-cluster lasers are below 0.5. Some time traces when you have a comparison of a global system and a cluster system. For example, 1 and 2 belong to the first cluster, to the unique cluster upstairs, and 1 and 2 in the first cluster, 6 and 7 at the second cluster. You can see also by eye the change in the emission properties of these systems. And of course, the coupling parameter plays an important role in this discrimination of clusters, because if you have loosely connected fields, then you can identify this cluster operation. However, when you increase this coupling, then there is a pooling effect from the injection locking of these lasers, where they pull into one unique frequency with strong variations. So also in this case, such operation is kept for a specific injection ratio range. So to summarize this part, with a passive relay mediating element in such network, we have identified high level of global synchronization among 60 nodes, 2 cluster synchronization among 8 semiconductor laser nodes. Synchronized behavior has been presented to be consistent, however, with so desynchronization events are to be expected. Reducing the bandwidth increases the cross-correlation between the chaotic signals. Signal complexity is shown that is not affected by the reduced bandwidth that we measure. And such topologies, I imagine that they can find applications in transmission sensing or hardware authentication of legitimate users that use these devices to authenticate them in a network through their own hardware devices. Now, in the second part, which will be a little shorter, we have replaced this relay system with another laser, which is from the same bunch of these lasers that we have available. The condition for an active relay was to keep this biasing of this relay higher than the nodes. We have the same topology investigated before. Also the numerical model that one could introduce. There are plenty of works that have been evaluating this performance previously. We have discriminated now the operation of the hub laser, which is the central one, the mediating element, and the stars, where these are the ones that will get the injection from a common mediating element. Our target here is to maximize the synchronization potential, since we expect that the bubbling properties of the synchronization manifold will disappear, and this is done by minimizing also the frequency detuning of all the lasers. In a topology, a much simpler topology, when we include 2 nodes, where we have user 1 and user 2 with each laser and the laser hub, with appropriate conditions for same optical emission and same wavelength emission, we have an operation that the system, the laser emission is dependent on the bias that we apply on the hub laser, the central mediating element. Above its threshold, we can see that the spectral emission becomes unique, broadened, and this includes, in general, chaotic dynamics. In several applications, we are interested in conditions where we have broad emission of chaotic carriers with suppressed periodicities. And this is the case, for example, of biasing the hub laser for 13 milliamps. This will be the value that we use in the experiment. And for this value, we have a mapping of the synchronization potential of these 2 nodes for various injection strengths. In this topology, it is not necessarily to have a symmetric coupling between nodes and relay to nodes. You can see that also here, where we have more injected power to the node lasers rather than the other way around. We can obtain some cross-correlation values between these systems over 0.99. And this is a performance that has been observed for the full detected bandwidth of the signals. If we apply the same process as before and try to reduce the bandwidth, we can see that we can even improve this performance up to 0.996 when including a signal bandwidth of 5 GHz at the detection process. So this is a very high value of cross-correlation in such systems, probably the highest that has been reported so far. You can see some properties of the time traces between the 2 nodes. And this optimization for the bandwidth, after applying a digital filter, you can see that we have this curve, which is completely explained if we consider the processes that we introduce by electrical filtering at the output, which is the following. The change in the signal-to-noise ratio of the detected signals. For example, for the specific signals that we work with, we have almost 80% of their power spectral density within the first gigahertz, as well as for the noise. We know that usually the amplification, the amplified spontaneous emission noise of the EDFAs, which is a major contributor in the noise of such systems, is almost linear to bandwidth. So you can see that if you get a very rough estimation of this SNR, you can identify a region where you expect an optimized performance in terms of bandwidth. So another aspect that we can investigate in this topology is the correlation of the hub emission to the node emissions. We can see that for specific values of the hub's laser current, we can always have a minimized cross-correlation with the output nodes. This changes, of course, when we change also the ratio of the injection and the biasing of the semiconductor lasers that act as nodes. However, in this performance, we can always find a very good cross-correlation among nodes, but not between the nodes and the hub laser. We can identify also in this measurement some leader-laggard dynamics, where the hub laser is always leading. This changed when we shifted to lower biasing currents for the hub and higher coupling strengths, but then in this condition we had a much lower cross-correlation value between the semiconductor laser nodes. This system can be extended to more nodes. It is straightforward as long as we upload many users in an appropriate one-to-n splitter. So we have tested that always for more. For 4 nodes, we have seen this table of cross-correlation values. We were always above 0.994. So we have a system with very high performance. And I will finalize just by introducing some application of these topologies, especially in the second part, where we achieved very high levels of synchronization between such elements of semiconductor lasers that are coupled in star-type topology. This synchronization, as I said earlier, was due to the inherent property of minimizing and eliminating the desynchronization events. Some of these applications that may be very interesting, and we have worked a little bit on that, was from desynchronized analog signals to generate some 2 random bit generators that are synchronized, to apply some communication protocols for secure communications, and finally, this is something at the end, just introduce their properties in the tasks that we are able to follow during this Centurio project for reservoir computing. So for the synchronized gigabit per second 2 random bit generation, it is a straightforward process to simply sample this analog signal that you get at your output and get some properties, get some binary sequences that you try to fulfill the randomness criteria set by different institutes that evaluate randomness. One condition that we had fulfilled earlier in our active topology was to have this type of spectrum with, as I said earlier, minimized periodicities in the emitted profile. So these types of spectral responses from signals, after appropriate downsampling, of course to eliminate some neighboring collaborations from neighboring samples of the sampling process, they can lead us to the generation of bit sequences that are obtained from synchronized analog waveforms, and after digitization they may fulfill these randomness criteria and be able to provide some synchronized random number generations at speeds that are very, very fascinating in terms of the current state of the art that is used in modern telecoms. Of course, in this case, the error rate, even if you see a cross-correlation value of an analog signal of 0.996, if it is converted through a simple sampling procedure, this turns into an error rate of 0.04, which it seems like bad, but if you use all these forward error techniques, that you can improve synchronization, then you can get to the second applications that I am going to introduce, which is the use of these synchronized through random bit sequences in communication protocols. One of the oldest communication protocols I will refer to, which is the one-time pad, which means that you use 1 bit of key for 1 bit of information and make that encryption. It is patented from almost the First World War. It's very old. However, the implications in these concepts is that you need bit keys, digital keys that are as fast as your data you're sending, which means gigabit per second in the modern communication technology. So if we employ such synchronized keys that we have generated earlier with this topology, the networks with the semiconductor lasers that emit these broadband signals, we can use as synchronized keys these sequences, and by the use of forward error correction, we can achieve 1 gigabit per second communication encrypted by the one-time pad protocol with error rates that are almost error-free at this bit rate. And closing today's presentation, just a few words about what we are trying to do in our next project, which is this improvement project. This is the description and the site that you can find that also uploaded in IFISC. We will try to use these components and the whole concept of reservoir computing as intelligent, high-speed methodologies in data traffic management of broadband optical signals. And I will be very short on that for a few minutes to show that one current property that we need to improve in contemporary optical networks is the term called latency, which is the delay between the initial simulation and the response, the sharing between the transmitter and the receiver. You can imagine that transmission delay in optical fiber is almost 5 microseconds per kilometer. But however, if you make a ping connection from the University of Islas Baleares here to Palma central offices, you can see that the ping time is should be around 50 microseconds. You can never get it below 50 or 30 milliseconds. One reason for that is the limitations we have in optical switching, because in metropolitan areas we may have to switch wavelengths, as I said earlier, lambda 1, lambda 2, in order to get to the right place. And by improving this value by orders of magnitude, it will be for some people a game changer, as they say, in high performance computing, online gaming, or trading, where even 1 millisecond makes $1 million. So we identify, even at this period of time, traffic bottlenecks at switches, and this makes a huge cost because we need probably sometimes extensive data buffering of data that are awaited to be forwarded in these switches. And during crisis, delays of ping measurements can even reach seconds. So one problem that we had initially was on the physical device. Usually traditional optical switches were operating under millisecond regime. However, with electro-optic methods, lithium niobate materials, all perovskite materials, we have now reached components that operate with fundamental frequencies of tens of nanoseconds. So this may be a huge improvement in data traffic networking. So what is the catch now? Besides the physical device that we need to correspond to such times, we need also the identification of header and all the analysis in order to make this switch change wavelength, which is under the name control. So the control mechanism of the switches include basic threshold evaluation bit by bit of the headers, but not intelligent mechanisms that almost could also avoid making this optoelectronic conversion in order to identify the header, remake the modulation, and then forward that to the switch and change the wavelength. So our project comes and gives, or will try to give, an answer on this intelligence of identifying and, if possible, making all optical control of the signals arriving at the switches and being able, even by single threshold detection, to make them work at the nanosecond or up to microsecond regime. For the reservoir computing implementations, I'm not an expert until now to follow many things. I mean, the group of Ingo has a very long experience on this work, where we can employ single lasers, for example, single nodes with complex behavior that will form a reservoir computing, and by just training the output weights of this reservoir, we can identify some outputs that will be helpful in making this decision process easy and fast. The amazing thing with this physical reservoir or photonic reservoir computing is that they have dynamics of nanosecond timescales, as the lasers that I showed earlier. So this is a property very unique to this very fast switching process that we need. This has been also in many works, also by people here in this group. And by finalizing this idea we have of this photonic reservoir computing that will be based always on some non-linearity. For example, this optoelectronic loop I showed earlier is based on Linkeda non-linearity. We got an optical input where we have multi-bit header patterns arriving in the reservoir. By making some classification processes, we can identify in a very fast way simple classes onto specific multi-bit header patterns. And these classes, they may represent in the actual physical system as voltage levels that will apply on the switch, and then we will have the control signal for the fast operation of this optical switch mode. Of course, there are more to come soon in this context. Thank you for your attention in this seminar. I hope I was not too dense. I believe I was, but it was enough for your information, and I will be happy to answer any of your questions.
Thank you very much. We had already a few questions during the presentation, but there's time for more.
In the active relay case, you see that there is a poor synchronization between the hub and the other laser. Is this just because of there is a delay, or there is something else? I mean, if you are measuring correlation at the same time, is this the case?
They are biased independently. I mean, while we're trying to make the same bias in the same conditions, providing the same conditions on the nodes, hub is an independent central unit that is controlled by someone else. So this asymmetry in the couplings also contributes to this difference in cross correlation.
One question.
Yeah, how flexible is to change the topology of the network? Is it possible to change? Because you have an all-to-all topology for the moment, can you manage to do something different in there?
You can change the symmetry, for example, by including in all paths, for example, an attenuator just to change the connectivity of the optical signal. But in a fixed topology as well.
The topology is fixed.
The topology is fixed.
You cannot change it.
It depends. What do you mean? You
Why
can.
it has to be a star topology? Doesn't have to, so it's not fixed.
And you cut one of the fibers and that's it. There is no
No, but you don't need to be a star. You don't need to be a star topology.
No, but there are limitations in the way that the experimental work can be done. I mean, you have to make an appropriate design.
That is much easier than connecting neighbors, for instance.
Not necessarily, because you can use 1 to 2 splitters and then
You can use different networks.
Yeah.
Other networks are possible,
Yeah.
but you have to use different kind of coupling, fiber coupling.
But now, for instance, when you couple the 8 elements, you have some, for example, you couple 2 to 1 and so on, you have some extra spare rings of fiber that could be used for additional couplings to other elements in a more
Very
different way.
One question I have myself, what you haven't discussed in your first part is the role of the delays in the star topology, because I assume that for example, fiber pigtails of the individual lasers are not identical. And while we know that this shouldn't have an influence on the stability, it will have an influence on the dynamics, right? Can you comment a bit on that?
Macroscopically, there was not such, I mean, it's not easy, you do not have so different emission between the lasers, but you do not expect something in terms of changing the synchronization. We have this round trip cavity length, which was plus or minus 12 centimeters, which is the difference that might be in each coupling path. So, of course, when you evaluate synchronization in these levels, you go not in a zero lag synchronization. You have a detuned lag, which is formed by the difference in the delay paths. But in terms of complexity, it is not easy to evaluate that experimentally. You will always have this change in the wavelength. So when this coupled in the equation with the detuning in the time domain, there might always be some alterations in the fixed wavelength that you are evaluating. So,
maybe one link then to what Pele mentioned. I think the configuration was also chosen because it is robust, for example, with respect to variations of delay, but it might also be very interesting going to different topologies and seeing how robust are networks with respect to heterogeneities and connection lengths. Because in other configurations this will be crucial.
Because you are scared of, if you see there, you have plenty of wings that are not used. Possible wings. Sure.
you can make it more complex. Isn't it?
Yeah, you could have other sort of topologies.
But don't forget that you also need the other ports to detect the light.
Well.
Yeah, you can always multiply the. Usually, the topology that you select should be driven on what you are trying to find and implement.
Are there more questions or comments? If not, let's thank Apostolos again.
Thank you very much.
And he'll be around for more questions.